All right, so now we're recording. Good afternoon, Anna, Jonathan, Charles, and Oriel. Thank you for joining me today. So ngayon, papagpatuloy natin yung paglalakbay natin para sa unit number 5, which is about integrals. Last time, we defined what the Riemann integral is, or how or when is a function Riemann integrable. We said that will happen kung siya ay yung lower Riemann integral saka yung upper Riemann integral. And the upper Riemann integral is the infimum of all the upper Riemann sums, while the lower Riemann integral is the supremum of all of the lower Riemann sums. Okay? And we said na medyo tedious yung pag-check kung Riemann integrable ang isang function or hindi. Kasi kailangan nating computein lahat ng posibleng upper sum at lahat ng posibleng lower sums para makompute natin yung kanilang infimum at supremum respectively. At kapag ka nag-equal yung dalawa na yon, so saka pa lang natin masasabi na Riemann integrable ang isang function. Alright? So we saw a couple of examples wherein we were able to use a definition para tingnan kung Riemann integrable, for instance, yung constant function, at saka ginawa rin ba natin yung linear function last time. So pero pagka komplikado na yung function, ang hirap niya nang gawin. Okay, for the reasons I stated earlier. So the goal of the next section is to establish necessary and or sufficient conditions for Riemann integrability. Ano yung mga properties na pwede naman nating gamitin in lieu of the definition para makapag-conclude whether a function is Riemann integrable? And we will start with Theorem 5.1, which might not look like a big leap from the definition ng Riemann integrability from last time, pero at least ito ay naka-phrase doon sa isang familiar question sa atin, which is about a challenge and a response problem. Okay? So how does it look like? So tingnan natin. Premise under Theorem 5.1, dapat si f ay bounded. Okay? And then f is Riemann integrable if and only if sa kahit anong epsilon greater than 0, however small it is, we can still find a partition inducer of the closed interval AB such that the upper Riemann sum minus the lower Riemann sum relative to that partition inducer is less than epsilon. So parang ito pa rin yung challenge sa atin dati, ano, na pag binigyan tayo ng epsilon, kailangan makapaghanap tayo. Dati delta ang hinahanap natin or capital N na starting index. Ngayon, ang hinahanap natin ay isang partition inducer. Isang partition inducer na napakalapit na nung upper mula dun sa lower Riemann integral to a point that their difference is less than the prescribed or the given epsilon in the beginning. So essentially, in layman's term, Theorem 5.1 can be phrased this way, na siya ay Riemann integrable if and only if we can make the upper and the lower Riemann sums arbitrarily close to each other. So kung meron akong question sa problem set na in your own words, sabihin yung Integrability Criterion Theorem 5.1, or I mean in layman's terms, yun lang yun. One sentence lang yung hanapin ko na yun. Huwag nyo na akong i-bombard ng napakahabang nobela. So hanapin ko lang naman pag sinabi nyo na, you can make the upper and the lower Riemann sum arbitrarily close to each other, then you'll get perfect credit for it. Huwag nyo na akong bulahin. Ano? Gusto ko direct to the point. Kasi yun din naman yung hanapin ko dun sa istorya na isusulat nyo. Ano? So yun yung sinasabi ng Integrability Criterion 5.1. Ang kagandahan nga nito operationalized yung pagiging equal ng upper at saka lower Riemann. Actually, hindi na pala natin kailangan hanapin yung upper at saka lower Riemann integral. Kasi yung kukunin pa natin yung infimum nito, kukunin ko pa yung supremum nito. Rito, kailangan lang nating magpakita ng isang partition inducer na totoo itong epsilon inequality na yan. So hindi man nalalayo yung itsura, pero ang laki ng burden na malilift from us when we go or when we try to compute, whenever we try to test for Riemann integrability. Okay? But before we can use this, kailangan i-prove muna natin siya. And this is an if and only if statement. So the proof is twofold, okay, or two parts. So simulan natin dun sa mas madaling part, okay? Ang una nating ipoprove ay yung pakabila. So may typo ulit dyan. So actually marami akong typo na na-discuss. So unahin natin na i-assume na sa kahit anong epsilon, nakakakita tayo ng partition or partition inducer na totoo yung epsilon inequality. And our goal is to show that F is I say mas madali ito, makikita nyo kung bakit, okay? So, ayun yung i-assume ko rito. This is our assumption for this first part of the proof. And then we will recall that the upper Riemann integral, kasi wala tayong choice so far kundi bumalik dun sa upper at saka lower Riemann integral, okay? Kasi hindi pa nga natin, yun pa lang yung alam natin para sa integrability. So I need to relate these two quantities with the upper and the lower Riemann integral so that magagamit natin yung definition ng Riemann integrability. But after this, probably we can go away with the upper and the lower Riemann integral just to establish integrability, okay? Now, ano nga ba yung upper Riemann integral? The upper Riemann integral is the infimum of the set of all possible upper sums. So, ibig sabihin, this is the greatest lower bound. Being the greatest lower bound, it is a lower bound in the first place. So, ibig sabihin siya ay mas maliit sa kahit na anong upper sum. In particular, it is smaller than the upper sum relative to the partition inducer we are considering. Okay? And analogously, the lower Riemann integral is the supremum of all of the lower sums. So since this is the supremum in the first place, it must be an upper bound. So this guy would be greater than or equal to any lower sum. All right? All good? Tapos ang alam natin dito, ang upper minus lower sum relative to P ay mas maliit kay epsilon. Etong minuend ay mas malaki kaysa sa upper integral. So kung papalitan ko itong minuend ng upper integral, so liliit yung minuend. Okay? Tapos, si lower integral ay mas malaki sa lower sum. So kung papalitan ko si lower sum by the lower integral, ibig sabihin lalaki yung subtrahend. Alright? So dun sa difference, lumiit yung minuend, lumaki yung subtrahend. So what do you think will happen to the difference? Makakakuha ako ng mas maliit na difference, right? So I replace this by a smaller number, the upper integral. I replace this by a larger number, the upper integral. So the difference of the upper minus the lower integral will be smaller than the difference of the upper and the lower sums. All right? Yung upper minus lower sum ay mas maliit sa epsilon. So the more na yung difference between the two integrals will be less than epsilon. Okay? And then we can also use the fact that we have proven that the upper integral is always greater than or equal to the lower integral. So we can say that this guy is actually greater than or equal to 0 din. Kasi nga yung upper integral laging mas maliit sa laging mas malaki kaysa sa lower integral. Okay? But I would like to remind you that this happens for all epsilon greater than 0. So this guy, this difference is a non-negative number, isa siyang non-negative number na mas maliit sa kahit na anong positive number. So if we go all the way back to Unit 1, meron dong result na nagsasabi na kapag ka meron kang non-negative number, I think it's lemma 1.1 if I'm not mistaken. May isang lemma doon na nagsabi na kapag ka meron kang non-negative number, na mas maliit sa lahat ng positive numbers, there's only one possible conclusion. That number is exactly equal to 0. And that's what we have over here. We have a non-negative number, which is smaller than any positive real number epsilon. So we don't have any choice but to say that this difference is equal to 0. Pag ito ay naging equal kay 0, ibig sabihin, equal yung upper at saka lower Riemann integral. Therefore, si F ay integrable sa closed interval AB. Tapos na yung unang part ng proof. Okay? Now, dun tayo sa mas exciting na part, yung forward direction. So, tayo pa uli ito, dapat forward direction. Ano yung forward direction? I-assume natin si F ay integrable. So, gusto nating ipakita na kung si F ay integrable, dapat meron tayong makikitang partition inducer na yung upper Riemann sum minus the lower Riemann sum is smaller than any epsilon. Okay? So, yun yung gusto nating ipakita. Alright? So, ang tanging assumption lang natin sa case na to ay si f ay integrable sa closed interval AB. So, the only conclusion that we know from there is that the upper ay equals sa lower Riemann integral. Okay? Tapos gagamitin ko ulit yung property o yung fact na itong mga to ay infimum at supremum na mga respective sums. Okay? So, ibig sabihin, babalik naman tayo sa unit 1 pa rin yata, characterization theorem ng infimum at saka supremum. So, kung si upper Riemann integral ay infimum ng mga upper sums. So ito ay infimum ng mga upper sums. So siya yung greatest lower bound ng mga upper sums. Kapag ka siya ay dinagdagan ko ng kaunti, nagdagdag ako sa kanya ng kahit napakaliit na positive number, yung sagot dun sa addition na yon ay hindi na lower bound. Kasi ito na nga yung greatest lower bound. So if I add to it a small positive number, say epsilon over 2, this guy, this sum, will not be a lower bound. Okay? So dahil hindi na siya lower bound para sa set ng lahat ng mga upper sums, there will exist at least one upper sum which is smaller than this guy. Kasi nga, yun yung magpapadisqualify sa kanya sa pagiging lower bound. So we can find a partition inducer P1 such that the upper sum of F relative to the partition inducer P1 ay mas maliit dito. Kasi nga, bawal na tong maging lower bound. Kasi ang greatest lower bound na ay ito, without the epsilon over 2. Okay? Now, ganun din yung argument ko para sa lower sum, para sa lower integral. The lower integral is the supremum. So it is the least upper bound. So being the least upper bound, if I subtract even a small positive number to it, the result will not be an upper bound anymore. So this guy, dahil nabawasan na yung LUB ng epsilon over 2, hindi na to pwedeng maging upper bound. So mali si lecture notes, dapat ito ay greater than. Okay? Kasi hindi na siya magiging upper bound. So dapat merong isang lower sum na mas malaki kesa sa kanya. Alright? So that means there will exist a partition inducer P2 such that the lower sum of F relative to P2 is larger than the lower integral minus epsilon over 2. Right? Tapos tingnan natin yung difference between the upper sum relative to P1 minus the lower sum relative to P2. Okay? So mangyari ulit, si minuend, papalitan ko by something larger. Yun yung nangyari dito. So medyo tumaas na yung minuend. Tapos itong subtrahend, papalitan ko siya nito, which is smaller than the original subtrahend. So the difference now involves a larger minuend, but a smaller subtrahend. So therefore, the new difference will now be larger than the original difference. The nice thing about this guy is this simplifies to epsilon. Why? Because we know that the upper minus the lower Riemann integral ay equal kay 0 because of the assumption that f is Riemann integrable. Okay? Now, don't get too excited yet because we're not yet done. Because the claim of the theorem is that there exists a partition inducer P such that the upper sum relative to that partition P minus the lower sum relative to the same partition P ay less than epsilon. Ang meron tayo dito, kamukha niya na, almost, but not quite there. Kasi ito ay upper sum with respect to P1, kasi ito ay lower sum with respect to P2. Magkaiba pa yung mga partition inducers na ginamit natin para magkaroon na less than kay epsilon. Pero thanks to the lemmas that we have established last time, madali lang tong remedyohan. Kasi instead of looking at P1 and P2 independently, kunin natin si P1 union P2. P1 union P2 is a refinement of both P1 and P2. All right? So tawagin natin P epsilon, yung P1 union P2. And again, P epsilon is a refinement of both P1 and P2. Tapos ano nga yung nangyayari kapag ka nagre-refine tayo ng partition inducer? Lumiliit yung upper sum, lumalaki yung lower sum. Okay? So ibig sabihin, kung papalitan ko to ng upper sum with respect to the refined partition inducer, So therefore, I'll get a smaller number. So liliit yung minuend. Tapos, kung papalitan ko si P2 by P epsilon, lalaki yung lower sum. So the subtrahend would be larger. So now the new difference, consisting of a smaller minuend and a larger subtrahend, ay magiging mas maliit dito sa original difference. So that means the upper sum minus the lower sum of f relative to the refined partition inducer P epsilon ay mas maliit dito. Pero ito alam na natin na mas maliit kay epsilon. So therefore, this guy is less than epsilon, which establishes our claim. Kasi pag binigyan ka ng epsilon greater than 0, ang gagamitin kong partition inducer ay si P epsilon, which was obtained using these quantities that we already know to exist. And that ends the proof. Kasi construction lang naman nung partition P that satisfies the epsilon inequality yung kailangan para sa theorem 5.1. Okay? So, any questions? Magano ko dito? Magsa-sound like ano ko, sirang lata rito. Sirang plaka. Paulit-ulit yung gagawin kong ano, yung mas maliit yung minuend, mas malaking subtrahend. So, yon. Usual argument to na posibleng magamit pa natin later. Okay? So, is everything good so far? Or naghang ba ko? Siguro late lang yung reactions, but I hope I'm still online. Okay. Thank you, Noriel. Hindi ko pala natuloy yung pag-shade. Kaya inaantay ko kasing lumabas yung shade dun sa screen ko. Hindi ko pala siya na-shade dun sa iPad ko. Kaya hindi siya talaga mag-appear dun sa screen ko sa laptop. But anyway, okay. So let's see it in action. Paano nagiging useful yung theorem 5.1 with a specific example. Now we show that the function, the identity function, f of x equals x, on the closed interval 0, 1 is Riemann integrable on that set 0 to 1. Okay, dito AB, dapat to ay 0, 1. Okay. Now, ang gagawin ko ay ganito. Magko-consider ako ng isang particular class of partition inducers. I will call the partition inducer P sub n to be the partition inducer consisting of how many? Consisting of n plus 1 points. Magsisimula kay 0, papunta kay 1, tapos ang step size sa pagitan ng dalawang points or dalawang partition points ay 1 over n. So from 0, you go to 1 over n, then to 2 over n, to 3 over n, hanggang makarating ka sa n over n, which is 1. So yun yung tatawagin nating partition inducer P sub n. Now, sabi ng criterion 5.1, kailangan lang tingnan natin ano yung behavior ng upper sum minus lower sum. And luckily for us, we will see later that considering this class of partition inducers will be enough to conclude that f is Riemann integrable on the closed interval 0, 1. Okay. Bakit? Kasi if we take a closer look, kunin natin yung difference ng upper minus lower Riemann sum. So you can expand the formula. So remember, this is the sum of the supremum over the ith subinterval times delta x sub I. Tapos yung lower sum naman, summation naman siya ng mga infimum times the step size, all right, or the length of the ith subinterval. Then if we subtract them from each other, we can use the properties of summation na masulat siya in this nicer form or this more compact form. So you can now remember this formula. Ito lagi yung formula natin para sa upper minus lower Riemann sum. Okay? So straightforward naman yung pagkaka-define ng formula na ito. Now, compute natin ito. So ano yung supremum on the ith subinterval? Remember, the ith subinterval will be the interval x sub I minus 1 hanggang kay x sub I. Tapos linear function to, f of x equals x. So increasing yon, ano? So ibig sabihin yung maximum on the ith subinterval will reside on the rightmost function on the rightmost point of the interval. Tapos identity function lang to, f of x over x. So ibig sabihin ang supremum dun sa ith subinterval ay yung function value ni x sub I, which also happens to be x sub I itself. The same thing goes for the infimum. That will just be the left endpoint x sub I minus 1. Okay? But x sub I minus x sub I minus 1, this difference is just the length of the ith subinterval. So therefore, this difference turns out to just be the summation of the squares of the ith subintervals. Okay? Tapos, alam natin by choice, by design, ang delta x sub I na haba ng bawat interval ay 1 over n. So delta xi is 1 over n, square it, you're gonna get 1 over n squared. Since 1 over n squared is independent of the indexing variable, pwede ko siyang ilabas ng summation. Okay? Tapos magsasum up lang ako dito ng ilang ones, ng n na 1. Kasi yung summation ay going from 1 to n, so ang total nito ay n. So magkakaroon ako ng n over n squared, 1 over n. So kapag kada nag-consider ako ng isang partition inducer na ganito yung itsura, na ang step size ay 1 over n, ang upper Riemann sum minus lower Riemann sum ay laging 1 over n lamang yung sagot. Okay? Tapos pag binigyan tayo ng kahit na anong epsilon greater than 0, I can always find a little n such that 1 over n is less than epsilon. Do you guys remember kung bakit totoo yun? Nabigyan ako ng kahit anong epsilon greater than 0, alam ko makakapili ako ng little n na natural number na ito ay magiging less than epsilon. What's the name for that principle or for that property? Tandaan niyo pa ba? Thank you, Jonathan. That's perfect. And Charles, yeah, yun yung Archimedean property. Di ba? Pag meron kang epsilon greater than 0, kahit gaano pa yung kaliit, laging may natural number that is big enough so that 1 over n will be less than epsilon. So that means, just looking at this particular class, we can always conclude that we can make u minus l very, very close, very, very close to 0. Because there's always a small n such that this is less than epsilon. Okay? So that means by the integrability criterion, Riemann integrable, si f of x equals x sa interval 0 to 1. Okay? So hindi ko kailangan mag-compute ng infimum at supremum ng upper at saka lower Riemann sums para lang ma-compare sila kung equal silang dalawa sa isa't isa. So that's the beauty of the integrability criterion of theorem 5.1. And it's an if and only if statement. So if you cannot find a partition inducer, or it is impossible to find such a partition inducer for some epsilon greater than 0, then you can conclude that f is automatically hindi na Riemann integrable. Alright, so tingin tayo, ano pa yung mga posible natin kayang sabihin? Ano? So halimbawa, meron naman akong function na bounded in the beginning ang alam ko. Pero dapat sa closed interval AB. Yeah. So kung si f ay bounded sa closed interval AB, tapos dagdagan mo pa ng continuity, then that is sufficient to conclude integrability. But this theorem 5.2a is not an if and only if result. So kapag ka siya integrable, hindi necessary na siya ay continuous. Okay? Ang sinasabi niya lang, kapag ka ikaw ay bounded at saka continuous, ibig sabihin integrable ka. Hindi necessarily totoo yung converse. Also, if f is bounded and it is monotonic, either monotonic increasing or decreasing, then f is also integrable on AB. And this is a godsend, or these are godsends, kasi ang bilis mag-check ng continuity at saka monotonicity. Pagka na-satisfy yun, bye-bye na sa upper at saka lower Riemann sums, alam ko na integrable na siya kaagad. Okay? Pero again, before we can use these assertions, kailangan i-prove muna natin sila. And the proofs are actually quite amazing. Tingnan natin kung paano sila isinulat. Umpisa natin sa statement A. Kapag ka raw si f ay continuous. Okay. So ano ang alam natin? Si f ay continuous at bounded. So yun yung dalawa natin pwedeng magamit para siguro gamitin natin yung integrability criterion 5.1. Now, si f ay continuous sa closed interval AB. Now, meron tayong theorem na kapag ka si f ay continuous sa isang compact set, then si f ay uniformly continuous na sa compact set na yon. All right? So that's what the second statement is saying, is telling us. continuity on a compact set is sufficient to conclude uniform continuity on that compact set. And ang closed interval naman, alam natin ay closed and bounded, therefore it is compact. Alright, so that's fine. Tapos gagamitin ko, ano naman ngayon kung si f ay uniformly continuous? It says that sa kahit na nung epsilon greater than 0, lagi tayong makakakita ng delta greater than 0 such that kapag ka si x minus y ay may absolute value na mas maliit na kay delta, then si absolute value of f of x minus f of y ay merong epsilon inequality. In particular, I will choose that to be less than epsilon over b minus a. Kasi di ba supposedly epsilon yan sa definition, but epsilon is an arbitrary positive number. If I divide it by a constant b minus a, then this will also turn out to be a positive arbitrary real number. Okay? So yun yung pinili ko. Tapos you will be thinking, what the hell? Bakit pinili na si epsilon over, bakit epsilon over b minus a yung pinili rito? Bakit hindi na lang epsilon? Ano? Makikita nyo, magmamagic na naman ako later. Ano? Kasi remember, para sa integrability criterion, ang kailangan natin ay upper minus lower less than epsilon. So, kailangan ko ma-meet yung epsilon na burden dito sa kanan. Alright? So, iwan muna natin yan. Makikita natin kung bakit siya magkakaroon ng b minus a or bakit mawawala yung b minus a mamaya. Okay. Now, kailangan nating humanap ng partition inducer P such that this is true para magamit SIP 5.1. Now, ang gagawin ko ay, meron ako ngayong given delta. Alam ko na yung delta ay nag-e-exist kasi nga may challenge na epsilon, laging may nag-e-exist na delta. Okay? So ngayon, ang gagawin ko, pipili ako ng kahit na anong partition inducer such that the lengths of all the subintervals will not exceed delta. So of all the class of partition inducers, pipiliin ko lang or pipili ako ng isang partition inducer na masyado nang maliit yung bawat subintervals. Okay? Na mas maliit na kesa dun sa delta na nakuha natin mula dun sa uniform continuity. So connected yan, dalawa na yan ha. Hindi ito out of the blue, nag-isip ako ng delta. This delta is the same delta na nandito sa uniform continuity. Okay? Tapos, so, yan. Tapos remember, para makuha ito, kailangan ko malaman kung ano yung itsura ni M, ni capital M minus little m. Kasi remember, ito ay equal sa sum ng mi minus mi delta x sub I, right? So we need to look at what's the maximum and the minimum, or what is the supremum and infimum of the function values inside of that subinterval. Okay? Ang kagandahan dito, alam natin by assumption na si f ay continuous sa closed interval AB. So ibig sabihin, continuous siya sa kahit na anong subset ng closed interval AB, including all of the subintervals. Alright? So si f ay continuous din sa closed interval na to, which is compact. Tapos sabi ng Weierstrass theorem o ng extreme value theorem, kapag ka si f ay continuous sa isang closed interval, then it will attain its maximum and minimum at a number in that interval. So ibig sabihin, there exists an x sub mi and an x sub little mi such that yung function value nito ay equal dun sa supremum, ang function value nito ay equal dun sa infimum. Okay? So ibig sabihin lang nun, yung maximum at minimum ay function value doon sa loob ng closed interval x sub I minus 1 at saka x sub I. Okay? So that means, yung kailangan natin dun sa u minus L na formula ay ito, ay pwede ko na pala tumburahin, ay ito, okay? Equal lang siya sa function value ng isang x sub little mi at saka, x sub capital Mi at saka x sub little mi. Okay? So, yun yung alam natin so far. Wala pa to. Pero, by choice, by the design of the partition inducer, yung haba nung ith subinterval ay hindi lumalampas ng delta. So, ibig sabihin, yung pagitan ng maximizer at minimizer ng function f doon sa closed interval, dito sa closed subinterval na to, ay hindi lalampas ng delta. Because ang total length nito ay delta, so ibig sabihin itong dalawa, nasa loob siya ng interval na to, so yung distansya sa pagitan nilang dalawa ay hindi lalampas ng delta. And this delta is the same delta na ginamit dito sa uniform continuity. Dahil meron akong dalawang x's na hindi lumampas ng delta yung difference nila, mag-hold ito sa kanilang mga function values. So therefore, function value siya ni x sub mi, function value siya ni x sub little mi, yung difference na to ay hindi lalampas ng epsilon over b minus a. Okay? Ang daming pinagdaanan, no? Pero there, nakita na naman natin si epsilon over b minus a. Now, we're ready to assemble the pieces together. Kukompute natin yung upper minus lower sum, and we are praying that this is enough, we have chosen our partition inducer nice enough that this will be less than epsilon. Okay? So I'm going to expand using the definition or using the formula we have for u minus L. Ito yung makukuha ko. Oh, tapos alam ko na itong mi minus mi, this guy is less than epsilon over b minus a. So I can replace this by epsilon over b minus a and get a larger number. And then this guy is independent of I. Pwede siyang lumabas sa harap ng summation. Ito yung makukuha ko doon. Okay? Eh ano nga ba itong summation na to? Itong summation na to, yan yung sum ng mga haba ng bawat sub-intervals. Pero meron nga tayong partitioning. Paano natin define yung partition inducer? Dapat yung partition niya na ini-induced ay para dun sa buong interval. So the sum of the lengths of the sub-intervals ay dapat ay length ng buong interval AB. Gaano kahaba si AB? B minus A. And there you go. B minus A divided by B minus A equal to 1. Yay! Naiiwan si epsilon doon. So what we have shown here is the possibility of finding or constructing a partition inducer such that its upper minus lower sum is less than epsilon. And that ends the proof. Sapat na ikaw ay continuous at bounded para maging integrable. All right? Questions? Ang daling sundan ng proof, no? Pero ibang feels kapag ikaw yung magsusulat from scratch, ano? So, yeah. And usually natrethreaten na yung mga students na, "Oh nga sir, kaya namin gawin 'yan or kaya nating basahin 'yan." Pero pag kami na lang po yung gagawa, mahirap magsulat ng proof, ano? Pero I think writing proofs is really a skill that you cannot learn by simply reading text, ano? Kasi walang foolproof way of writing a proof. So kailangan mo talagang magkaroon ng instinct kung paano mo i-attack ang isang problem, and the only way that you can develop an instinct ay paulit-uliting gawin ito. Gawin siyang isang menial task na lamang o isang muscle memory thing para magkakaroon kayo ng idea na pag nakita niyo yung theorem, mukhang ganito yung pwedeng approach. Okay? So kailangan try pagsusulat ng proofs or kahit pagbabasa ng proofs, because you can pick up certain skills sa pagbabasa ng proofs. And when I say pagbabasa ng proofs, critique ng isang proof, pag-i-insert ng mga missing details sa isang proof, katulad ng ginagawa natin ngayon. Alright? Now let's try to prove the other assertion that being bounded plus monotonicity is sufficient for Riemann integrability. Okay, so without loss of generality, I will assume that f is increasing. I can do so because I can easily tweak the proof that I will present kung si f naman ay decreasing. Okay? So kung si f ay increasing, so ibig sabihin yung minimum ni f ay function value nung left endpoint. Kasi nga increasing siya. So ang pinakamababang function value ay manggagaling dun sa pinakamababang x. So kay f of a yon. Tawagin natin yung minimum na yon na little m. Tapos yung maximum, dahil si f ay increasing, ay magaganap dun sa pinakamalaking x value, yung nasa kanan, which is b. So f of b is the max, tas tawagin nating capital M ito. Now, if your function is decreasing, mababaligtad lang. Si little m ay f of b, tapos si big M ay f of a. So yun lang yung mababago, and the entire proof will hold true. Okay? Now, mahati yung proof sa dalawang cases. Makita nyo mamaya kung bakit. Pero yung unang case ay si little m ay equal kay capital M. Ibig sabihin, parehas yung maximum at saka yung minimum. Nangyayari lamang na equal yung maximum at saka minimum kung si f ay constant function. Right? So, if f is a constant function, we already know that this is Riemann integrable. Na-prove na natin ito last time. Right? So, ibig sabihin, we're done kung si f ay constant. Pero kapag si m ay hindi equal kay capital M, meaning little m is smaller than capital M, then kailangan natin magsulat ng isang mas rigorous na proof. Okay? Now, gusto kong magamit ulit si Theorem 5.1. Okay. So, pag binigyan ako ng epsilon greater than 0, kailangan ko mag-imbento ng isang partition inducer such that this is less than epsilon. Okay? So, the quandary here is, ano dapat yung partition inducer na piliin ko para mag-guarantee na ito ay mas maliit kay epsilon? So you need to put your thinking caps. Tapos, hindi, wag na lang. Mapapakanta ako ng Blues Clues eh. Hindi ko alam kung nabutan yung pa yung Blues Clues. Pero paborito kong kinakanta yun dati nung kabataan ko. No? So, yun. Dapat pala meron ako dito i-play, no? Sayang. Okay. But anyway, so we need to define a partition inducer. And the text is telling me that, piliin mo yung partition inducer such that yung haba ng bawat subinterval ay hindi lalampas ng epsilon over capital M minus M. And again, we'll be scratching our heads. Saan nanggaling yung over yung M minus M? That will appear later, okay? Now, and this will also tell you, why do we need to have two cases for the proof? Because this argument will not hold if capital M is equal to little m. Because if that's the case, then the denominator will be equal to 0. Magkakaroon ng butas yung proof natin. Okay? So kaya inuna na i-prove kapag si m ay equal kay m. So at least now, we are sure that m minus m is not equal to 0. And further, since m is the minimum, it is strictly smaller than m. So the denominator here is positive. Okay? And epsilon is assumed to be positive, so this guy is positive, so everything makes sense. All right? Now, so yan daw. So i-check nga natin, tama ba itong choice ko ng partition inducer P? So tingnan ko yung U minus L. Pangarap ko maging less than epsilon yan. Now, using our formula para sa U minus L, ito lamang yan. Tapos, alam ko yung delta x sabay, pinili natin so that hindi siya lalampas ng epsilon over m minus m. Okay? Tapos constant siya with respect to I. So lalabas lang siya nung summation. So makukuha ko ito. Ano yung matitira sa loob ng summation? Capital MI minus little mi. Right? Where capital MI represents the maximum on the ith subinterval and little m sabay is the minimum on the ith subinterval. Okay? So sila yung maximum at minimum sa x sabay minus 1 hanggang x sabay. Okay. So kailangan ko siyang i-expand. So anong itsura ni little m, ni capital M minus little m sa bawat interval? Well, si f ay increasing, di ba? So si f ay increasing, so therefore ang pinakamalaking function value ay nandito sa right endpoint. So capital Mi is equal to f of x sabay. Meanwhile, the smallest function value will occur at the smallest x value. So little m sabay is the function value at the left endpoint. Okay? Tapos, simplify natin itong summation na ito. Expand ko siya. Kapag kasi I ay 1, meron akong f of x1 minus f of x sub 0. But f of x sub 0, remember, is what? F of x sub 0 is f of a. Tama? Tapos kapag kasi I ay 2, magkakaroon tayo ng plus f of x2 minus f of x1. Okay? Tapos kapag kasi I ay 3, I'll have f of x3 minus f of x2 all the way up to when n is equal to n, we're gonna have plus f of x sub n. Pero ang f of x sub n lamang ay f of b minus f of x sub n minus 1. Alright? Tapos ito, magte-telescope yung mga terms. Kasi may f of x1 ako dyan, may minus f of x1 dito. Meron akong f of x2 rito, pero may minus f of x2 dyan. The process will go on until all that remains would be f of b minus f of a. But what is f of b? F of b is capital M. F of a is little m. So therefore, this summation is just capital M minus little m. And that is the purpose of including a denominator in our choice for the upper bound for the lengths of each of the subintervals. All right? Para ito, makancel na to, matira, yay, epsilon na lamang. Okay? And then we're done. Because epsilon was chosen arbitrarily, we're able to construct a partition inducer that will make U and L within epsilon units of each other. And so we're done. We have proven na ang monotonicity ay sufficient together with boundedness para makonclude ang Riemann integrability. Okay? Sige, hinga muna tayo ng konti. Absorb natin. Okay. Tingnan natin. Next result. So, dinadamihan na natin yung mga kailangan. Right. Now, before we going to the next result, we note that the previous theorems will tell us na, okay, eto na, lalabas na yung mga iba nating results. Lahat ng continuous function na bounded sa isang closed interval, lahat ng monotonic function sa isang bounded sa isang closed interval, lahat sila ay Riemann integrable. So that includes any polynomial, okay? Tapos any trigonometric function, of course, on their domain. Tapos exponential functions dahil bounded sila sa closed interval, sa isang closed interval, tas continuous sila. So ibig sabihin ito ay Riemann integrable, okay? Tapos si e to the sin x being the composition of two continuous functions will be continuous on a closed interval AB. Tapos bounded din siya doon. So ibig sabihin ito ay Riemann integrable din. Okay? And then also we have the floor function, which we know is discontinuous at any integer, pero dahil siya ay increasing sa isang closed interval, so kahit siya ay discontinuous sa mga integers, kahit magkaroon pa ng integer dun sa isang closed interval na kinoconsider mo, ang kailangan lang kasi ay boundedness plus monotonicity, then ito ay Riemann integrable din, kahit siya ay discontinuous. Now, that brings us to another question. Ano nga ba yung misteryo sa mga discontinuous functions? Bakit yung ibang discontinuous functions ay integrable at yung iba ay hindi? So we need to probe. Ano dapat yung klase ng discontinuity, or up to what extent your function should be discontinuous or can be discontinuous on a closed interval para siya ay manatiling integrable pa rin? Okay? The baby answer to that question is Theorem 5.3. Sinasabi ng Theorem 5.3, kapag ka daw si f ay continuous sa closed interval AB, mapwera sa finite number ng mga pasaway na points z1, z2 until cn, then si f ay integrable pa rin. So pag may mga nagrebelde na points na finite lang naman sila, kokonti sila, kahit mga 31 million sila, pero kung dun discontinuous yung function, dun lang siya discontinuous, ibig sabihin, integrable pa rin yung function. Okay? Yun yung ipoprove natin ngayon. So kung finite lang yung number ng points of discontinuity, si f ay Riemann integrable pa rin sa isang closed interval AB, which speaks volumes, na basta finite, kahit discontinuous, okay ka pa rin. So radical kasi yung pagiging integrable. So basta finite yung hindi ka discontinuous, then yun. All right. Oh, nakuha ni nice one, Charles. Okay. All right. So tingnan natin yun. Tingnan natin yung proof kung bakit siya totoo. All right. So i-assume ko rito na si Z1, si Z2 until si Cn ng mga points of discontinuity ay naka-arrange in increasing order. So kumbaga kung ita-plot ko siya, actually mas madaling tingnan yung proof ng graphical, So ito si A, ito si B, tapos meron ka ditong Z1, Z2, Z3, hanggang kay Zn. Okay? So naka-increasing order na yung mga points of discontinuity. Gamitin ko capital N. Okay? Tapos, ang gagawin ko ay, ang gusto kong gamitan ay si Theorem 5.1. So, pwede akong pumili ng isang specific partition inducer relative to a given epsilon greater than 0. So, given na muna si epsilon greater than 0. Pipili ako ng partition inducer. Tapos, ang sasabihin ko, pipiliin ko yung partition inducer na nakadepende sa isang number delta. Okay? Ano si delta? Si delta ay yung minimum ng mga numbers na yan. Kamot na naman tayo ng ulo kasi, bakit na naman may epsilon over 8mn dyan? Pasikat talaga yan, sir. Tapos may z1 minus a over 3, z2 minus z1 over 3. Where the hell do those numbers come from? Ano? Saan sila nanggaling? Well, balikan natin yung assumption. Si f ay bounded. So, si f ay bounded, ibig sabihin merong isang positive number m na mas malaki sa lahat ng absolute value ni f of x sa buong interval AB. So siya yung nandito na capital M. Si capital N, siya yung bilang ng mga points of discontinuity. Kaya importante sa theorem na to na finite yung number of points of discontinuity para alam natin ano si capital N. Kasi kasama siya sa pagde-design ng partition inducer P. Tapos, itong mga to ay, ito ay magagaranti na yung delta neighborhood na centered kay Z1 ay hindi lalampas kay A at hindi rin siya makakarating kay Z2. Right? So ang idea kaya meron diyang mga over 3 ay para ganito. Para makulong yung bawat C sub n sa isang delta neighborhood na wala ng ibang lamang point of discontinuity. So yung delta na mapipili natin will be something like this. Oops. Ito yung isang delta. Ito yung delta. Ito yung delta. Okay? Nagagaranti niya kasi yung delta ay mas maliit kaysa sa Z1 minus A over 3. So yung delta neighborhood sa kaliwa ni Z1, hindi niya madadali si A. Right? So hanggang dito lang siya. Tapos dahil si delta ay mas maliit din sa Z1 minus Z2 all over 3, so ibig sabihin itong delta neighborhood or yung part ng delta neighborhood sa kanan ni Z1 ay hindi lalampas na mapapasama pa si Z2. Yun yung dahilan kung bakit ganun ko pinili si delta. Kung bakit hindi siya dapat lumampas doon sa Zi minus C sub I minus 1 all over 3 para nakakulong yung mga points of discontinuity sa loob ng isang delta neighborhood. So dyan lang muna sila. Silang 31 million sila, isolate muna natin for now. Tapos saka natin sila isasama mamaya pagka nandun na tayo sa exciting na part ng Theorem 5.1. So etong mga partition inducers na yan, oops, sorry. Okay. Kulayan ko sila. Gawin natin silang mga dilawan. So yan. Masyadong malaki. Kulayan ko na lang siya ng Kulayan ko na lang siya ng yan. Ito, yan. Kung saan sila nakakulong. Yan yung tawagin natin mga yung union ng mga yellow intervals, sila yung tawagin nating P sub 0. So alam natin, si function f ay hindi continuous dun sa yellow intervals. Tapos kulayan natin ng pink, yung mga nandito yung nasa pagitan. Okay? Na nasa pagitan ng mga dilaw na intervals. And what we know dun sa mga pink intervals, yung function f ay continuous dyan sa mga pink intervals na yan. Tawagin natin tong E1, tawagin natin tong E2, E3. So si f ay continuous sa bawat isang mga E1, E2, E3, and so on. Dahil continuous si f sa bawat E sub I, okay? So ibig sabihin si f ay integrable sa bawat E sub I. Yun yung sinabi ng theorem natin kanina, 5.28. Alright? So continuous si f doon sa mga E sub I. So ibig sabihin, we can find a partition inducer of E sub I such that the upper Riemann sum of f relative to P sub I minus the lower sum f of f relative to the partition inducer P sub I. Pero mind you, si P sub I dito ay partition inducer ni E sub I. Doon lang siya nagwo-work sa doon sa mga subintervals kung saan continuous yung ating function f, right? And I can make it close, very, very close. How close do I want them to be? I want them to be close within, kailangan ko ng kodigo ko. Yon, epsilon over 2 times n plus 1. So gusto ko bawat isang to ay within epsilon over twice the number of number of discontinuity points plus 1. All right? Kaya lang, kaya ko lang itong gawin dun sa mga pink na intervals. Dun sa mga dilawan, kailangan ko pa ng konting analysis para sa kanila, no? So, ang gagawin ko ngayon ay, titingnan ko, ano yung nangyayari ngayon? I-relabel ko lang yung partition inducer na gagamitin ko para dun sa malaking set. So, si A, tatawagin ko siyang si T0. Yung unang boundary point, sino yung unang boundary point? Yung unang boundary point sa pagitan ng pink at dilaw ay si C sub I minus delta, right? Nasa gitna si C sub I kasi point of discontinuity siya. Pero delta neighborhood yan, so ito ay Z minus 1 delta. Si C sub 1 minus delta, siya yung gagawin kong T1. Tapos yung pangalawang subdivision point, siya yung gagawin kong T2. Pangatlong subdivision point, si T3. Tapos ito si T4. So ibig sabihin yung mga T sub I's, except T sub 0 and T sub n, sila ay yung mga C sub I either minus delta o C sub I plus delta. Ang dulo lang dito ay ito si T sub little n. So si set T0 hanggang si set T sub n ay isang partition inducer nung buong interval. Okay? Yun nga lang, yung partition inducer na yon ay nakakagawa ng dalawang klaseng subintervals. Pink na subinterval, yellow na subinterval. So if we will compute the upper Riemann sum minus the lower Riemann sum relative to the partition inducer T0 to Tn, pwede natin yung hatiin sa dalawang parte. Okay? So ito na. Si P ay yung collection ng mga T sub I's. So yung upper Riemann sum minus lower Riemann sum of F relative to the partition inducers T0, T1, T2 hanggang Tn ay pwede kong hatiin sa dalawa. Yung upper minus lower Riemann sum mula dun sa dilaw na interval plus yung upper minus lower sum na nanggagaling naman dun sa pink na subintervals. Okay? So, tas ko-compute natin sila na magkaiwalay. Tas saka tayo magkakaroon ng unity. Mapapakita natin na less than epsilon yung sum ng mga yan. Alright? So, paano? Umpisa natin dun sa second term. Dun sa mga pink na intervals. Ano? Dun sa mga pink na intervals, okay, by definition, this is basically just upper minus lower Riemann sum ng mga pink na intervals. But we already know that each of the, dun sa bawat isang pink interval, yung upper minus lower sum ay hindi lumalampas ng epsilon over 2 times n plus 1. So that means this guy will be replaced by this guy and I'll get a larger number. Okay? Tapos ito ay independent ng I. Pwede siyang lumabas ng summation. Matitira lamang ay summation ng ones. I going from 1 to n plus 1. Pag meron kang n plus 1 na 1 na pinag-a-add, ang total nun ay n plus 1. So, yun. Kaya pala ako naglagay ng n plus 1 doon para makancel yung n plus 1 na manggagaling dun sa summation. So, magkakaroon lang ako ng epsilon over 2 na contribution mula dun sa 14 million na pink intervals. So, no, joke lang. Mula dun sa interval na yun. So, epsilon over 2. Tapos puntahan natin yung mga dilawan. Dun sa yellow intervals, eto naman yun. Okay? Kukompute natin yung MI minus, yung capital MI minus MI, right? But we know that F is bounded. And we said that F is bounded above by this guy, all right? Bounded above by M. This can be translated into discontinued inequality, F of X, M. So, pinakamaliit niyang value ay M, pinakamaliit niyang value ay negative M, pinakamalaki niyang value ay m. So yung m sub I minus little m sub I, sure tayo hindi siya lalampas ng 2m. Right? Kasi ang pinakamalaking posibleng value nito ay m. Pinakamalaking posibleng value nito ay negative m. M minus m, 2m. So sure ako ito hindi lalampas ng 2m, kaya less than or equal yan. Okay? So that's good. Then t sub I minus t sub I minus 1. Ito yung length ng mga intervals, right? Pero sabi natin by design, ang haba ng bawat isang pink interval, bawat isang yellow interval ay 2 delta. Kasi ito ay delta dito, delta dito, delta dito, delta dito. So ang total niya ay 2 delta. 2 delta ang haba ng bawat isang yellow interval. So this guy is exactly 2 delta. Okay? So tapos, anong alam natin? So 2m, bababa siya dito, magkakaroon siya ng 2m. Tapos si delta was chosen so that it is the minimum nitong mahabang expression na ito. So ibig sabihin si delta ay mas maliit kesa kay epsilon over 8mn. So that means this guy, nasaan na tayo? So ito ay magiging 4mn. Pero si delta ay hindi lalampas ng epsilon over 8mn. Yun naman pala. Kaya merong mn doon. Para makancel, 4 over 8, epsilon over 2, yun. Epsilon over 2 rin. Epsilon over 2 plus epsilon over 2 equal kay epsilon. And what have we established here? Nakakita tayo ng partition inducer na yung upper minus lower sum ay hindi lalampas ng epsilon. And so that means our function f, even though it is discontinuous on a finite number of points on a closed interval AB, is still integrable on that interval. Okay? Yun yung nangyayari sa floor function. Kasi, di ba yung floor function, ganito yung itsura niya. Equal. Tapos dito ay, tapos ganito. Okay. So ganyan yung floor function, discontinuous siya. Pero pag tumingin ka lang sa isang closed interval AB, meron lang diyang finite number ng mga integers kung saan siya discontinuous. Dito ay isa, dalawa lang yung points of discontinuity niya. Or in other words, kung ilan yung integers sa pagitan ni AB, ganun lang karami yung points of discontinuity niya. Kaya kahit ano pang closed interval yung i-consider mo, laging integrable yung floor function. Kasi nga finite lamang yung points of discontinuity niya. All right. Then we have met another type of discontinuous function last time. Siya si Dirichlet function. Si Dirichlet function hindi siya nag-qualify dun sa theorem na ito kasi naman ang problema sa kanya siya ay equal kay 0, siya ay equal kay 1 kapag ka si x ay rational sa 0, 1, tapos 0 siya kapag ka si x ay irrational. Tapos na-prove yata natin na itong Dirichlet function ay hindi continuous kahit saan. Alright? So dahil hindi siya continuous kahit saan, dun sa closed interval AB, at there are infinitely many points on the closed interval AB, then hindi mag-apply sa kanya yung theorem 5.3. Kasi si theorem 5.3, kaya niya lang i-guarantee ng isang function ay Riemann integrability kapag ka finite lamang yung number ng kanyang points of discontinuity. Okay? Now, let's see. So, pero alam natin to ay discontinuous. Ano? So, meron palang limit. Alam natin siya ay hindi integrable. So, may limit lamang yung pag-aalaw natin na siya ay discontinuous. Alam na natin na as long as finite number yung kanyang points of discontinuity, then siya ay Riemann integrability pa rin. Pero pagka infinite na yung number of points of discontinuity niya, hindi na nakakita na tayo ng example, the Dirichlet function, kung saan siya ay hindi na Riemann integrable. So the nice question to ask is, how further can we push the exception doon sa pagiging continuous? Alam na natin pag finite continuous siya, pero pag sobra siyang infinite, hindi na siya magiging hindi na siya magiging integrable. So baka naman kaya pa nating i-push na hindi lamang finite yung discontinuity. Baka naman pagka may infinite or level ng infinity kung saan pwede pa rin maging Riemann integrable yung isang discontinuous function. Okay? Yun yung titingnan natin sa susunod na result. But to better understand this grand result, kailangan natin yung konsepto ng measure. Dinidiscuss talaga ang measure sa graduate level na. Sa Math 230 ko na siya unang na-encounter. Pero siguro yung mga applied math, pagka nag-stochastic processes kayo, Math 182, ay kakailangan ninyo na rin kasi doon ng konsepto ng measure. Paano natin sinusukat ang isang set, ang isang function, and so on. So, hindi ko masyadong habaan yung discussion about measure, pero ito lang yung measure, ito yung konsepto ng measure zero. Kailan natin masasabi ng isang set ang kanyang, ang measure natin sa kanya o ang sukat natin sa kanya ay zero. Now, a set is of measure zero if and only if for any epsilon greater than zero, we can find a family, a countable family of open intervals such that yung union ng mga open intervals na yon ay superset ni set A. So you can think of nako-cover nung union ng mga open intervals yung set A. So ibig sabihin, bawat isang miyembro ng set A ay nalalagay sa isang miyembro ng mga open intervals. So kung meron kang set A, isipin mo na lang tinatakpan mo yung set A ng mga elements ng open interval. Kung hindi mo na makikita si set A kasi natapalan na silang lahat ng mga open intervals, so we say that A is covered by the collection of open intervals. Okay? Pero ang challenge para maging measure zero siya ay dapat pagbibigyan kita ng budget na total lengths ng mga open intervals na gagamitin mo, you should be able to do it however that small budget is. So maliit yung budget mo sa total length ng subintervals. Epsilon greater than zero. Dapat lagi ka pa rin may mahanap na open intervals na makakapag-cover dun sa set na yon, such that yung sum ng mga lengths ng subintervals na yon ay dapat hindi lalampas dun sa budget na epsilon na binigay ko sa'yo. So that means a set is of measure zero if it can be covered by arbitrarily small open intervals. Saka siya magiging measure zero. Okay? Of course, hindi lahat ng sets ay measure zero. Right? Most of the interesting sets are those that are not of measure zero. For instance, any closed interval, ang measure ng kahit anong interval ay yung haba niya. Ang closed interval AB, ang measure niya ay B minus A. Open intervals, ganun din. Pero kapag meron kang isang finite set, A1 to A sub capital N, ito ay measure zero. Kasi ang mangyayari lang ay, kapag dinrawing ko sila dito, A1, A2, A3, A5, AN, okay? Pag binigyan ako ng epsilon greater than zero, kaya ko pa rin gamitin yung budget na yon para sa length, para ako nagda-draft pick dito or nag-fantasy football or fantasy NBA, na meron lang akong budget epsilon. Kailangan ko siyang humanap ng mga players na makakapag-cover ng A1 to AN na hindi ako lalampas dun sa budget na epsilon. No? So sabi rito sa example, kapag binigyan ako ng budget na epsilon, kaya ko mag-consider ng pang-cover dito sa A1 to AN, pipiliin ko lang itong interval A sub n minus epsilon over 2n hanggang kay AN plus epsilon over 2n. Clearly, bawat isang A sub I ay nandito sa O sub n. Tapos, gaano ba kahaba bawat isang O sub m? Bawat isang O sub n, ang haba niya lang ay epsilon over capital N. And there will be capital N of them. So the total lengths nung gagamitin kong pang-cover dito sa finite set na to ay equal kay epsilon. So that means this finite set has measure zero. In fact, any finite set has measure zero. Alright? May isa pang class na measure zero. Sila naman yung mga countable sets. Pag meron kang isang countable set, ibig sabihin countable siya, so ibig sabihin siya ay countably infinite. Okay? So, kasi yung finite case na consider na natin. Alam na natin ang finite sets ay measure zero. Kapag meron kang countable set, ibig sabihin kaya mo siyang masulat. Kaya mong mag-start magbilang, pero hindi ka matatapos magbilang. So, yun yung pagiging countable. Kaya mo siyang bilangin pero hindi ka matatapos. Posibleng hindi ka matapos pagbibilang. Alright? So kapag ito yung countable set ko, measure 0 pa rin yan. Kasi kahit infinitely many sila pero countable sila, so I can do the covering one by one in a nice manner. Okay? And so on. Makakahanap ako ng open intervals na center yung bawat isang member niya. Ang requirements sa measure 0 dapat countable yung set na ipapang-cover mo. Countable naman yung set E, tapos sa bawat isang set E, meron akong isang pang-cover, so yung total number ng mga pang-covers ko ay countable pa rin. So pwede pa rin to. Tapos pagdidesisyonan ko na lang gaano dapat kahaba bawat isang cover. Sa bawat isang cover O sub n, ang suggested length niya ay ito. Dapat ang bawat isang O sub n ay A sub n minus epsilon over 2 to the power n plus 2 hanggang A sub n plus epsilon over 2 to the power n plus 2. Now, each of these subintervals will have length what? Epsilon over 2 to the power n plus 1. And there would be infinitely many of them. So pag sinum ko yung haba ng bawat interval, dapat ito ay may subscript. So magiging ano lang siya, geometric series. Summation lamang ng 2 to the power n plus 1. Geometric series, countably infinite. Tapos gamitin nyo lang yung math38 powers nyo para pagko-compute ng sum ng isang geometric series. You will see that this sum will be epsilon over 2. And epsilon over 2 is less than the budget epsilon that were given to you earlier. So that means any countable set is also of measure 0. Okay? So at least may dalawa na tayong family ng mga sets na ang measure nila ay 0. Now, ano yung implication kapag ka measure 0 yung set nila? Well, dito papasok yung major theorem. Ito yung Lebesgue's criterion for Riemann integrability. Ang sabi ni Lebesgue, all right, if you have a function f on the closed interval AB, then that function f is Riemann integrable if and only if. So it's a nice thing. It's a conditional. It's a characterization theorem. If and only if kasi siya biconditional. So si f ay Riemann integrable if and only if the points of discontinuity of f has measure 0. May isa pa tayong tawag dito. Kapag ang isang property ay nangyayari sa buong set maliban sa isang subset na ang measure ay 0, ang tawag natin doon ay almost everywhere. So you can say na kapag si f ay hindi continuous sa isang set lamang na of measure 0, we can say that f is continuous almost everywhere. Almost everywhere kasi dun lang siya hindi continuous sa isang set of measure 0. So, yun yung sinasabi nito. Riemann integrable ka kapag continuous ka almost everywhere. Meaning continuous ka except sa isang set of measure 0. Okay? And this is an if and only if statement. So, covered dito yung 5.3 kasi sabi natin ang isang finite set ay measure 0. Dahil yung set na yun ay measure 0, so ibig sabihin by Lebesgue's criterion, integrable pa rin siya. Now, mas generic nga lang to kasi sinasabi niya, okay, pwede mo pa yung palakihin. Merong mga certain types of infinities na pwedeng maging Riemann integrable pa rin. Pag binilang mo yung points of discontinuity ni function f at siya ay countable infinite or countably infinite, then f is still Riemann integrable as long as it is continuous and bounded. Okay? So posible na meron kang countably infinite points of discontinuity, but other than that, f is bounded, then f is still Riemann integrable. So medyo malaki-laki na yung classes. Kaya lang si Dirichlet function, hindi talaga siya integrable. Hindi natin siya kayang ipilit kasi ito na si Lebesgue, sinabi niya na if and only if kasi ito eh. Kasi yung points of discontinuity ni Dirichlet function hindi measure 0. Si Dirichlet function ay discontinuous on the entire interval 0 to 1. The measure of the closed interval 0, 1 is 1. So therefore, it is not of measure 0. It's measure 1. So dahil si f, si Dirichlet function ay hindi continuous sa isang set of measure not equal to 0, then Dirichlet function is not Riemann integrable. So this is kind of general, right? Alam na natin na kapag continuous, siya ay integrable. Tapos alam na natin ngayon yung pakabaligtad. Siya ay integrable if and only if si f ay continuous almost everywhere. Okay? And I think this is a nice place to stop for today. Any questions? Parang sakto lang. Yeah. Parang may nakalimutan ba akong gawin? Kasi nag-overtime ako sa kabilang section eh. Tapos dito rin ako tumigil. Mukhang wala naman. Alright. I'll just announce na extended yung deadline ng homework. Right after we drop the call, I'll change it in Canvas and announce it via email. So ang deadline na ng homework 6 would be tomorrow. Okay. So it seems that you don't have any concerns. So okay, so we'll just continue on Tuesday. We'll start with the Archimedes-Riemann theorem, and hopefully discuss properties of integral. Now, starting from Archimedes-Riemann theorem, titingnan natin paano nagko-compute ng Riemann integral. Kasi so far, yung mga theorems natin ay nagsasabi kung kailan siya Riemann integrable. But I think we have sufficient knowledge na kung sino yung mga functions na Riemann integrable. So the next question is, how do we compute the Riemann integrable of Riemann, to compute the Riemann integral of Riemann integrable functions? So hopefully the Archimedes-Riemann theorem will give us some clues, and then yung mga properties din na makikita natin later. Okay? All right, so and then yung pala ibibigay ko yung yung last problem set on Monday, 8 a.m. Around 8 a.m. on Monday. You can now download the last problem set covering units 4 and 5. Though siguro may iba pang questions na hindi nyo pa masisimulan kasi baka sa Tuesday pa natin i-start i-discuss yung mga kailangan nyo para sa ilang items. But I urge you to start answering those problems that you can already answer starting on Monday. Bibigay ko siya, pero ang deadline pa rin niya ay June 9, last day of classes. Para yun na lang yung tanging may tutulong ko sa inyo kasi alam ko mabobombard na kayo ng mga deadlines in the coming weeks. Sabay-sabay kaming magbibigay ng deadlines. Pero mauna na ako, bigay ko na yung problem set as early as Monday, 8 a.m. Okay? Para pwede nyo nang unti-untiin para hindi siya sumabay dun sa sandamukal niyo pang problem sets sa padulo ng semester. Pero don't worry, the deadline is still June 9. So you have about 3 weeks para matapos yung huling problem set. And then I hope to get all of your outputs by June 9 para mag-guarantee na mabibigyan ko kayo ng grade bago yung deadline of submission of grades. If you're still behind, you can still submit after June 9, but I cannot promise that I can give you a numerical grade by the deadline. Okay? So kasi marami akong classes this semester, so marami akong dapat checkan, sabay-sabay sila, so ganun na lang. So my only promise is by all outputs by June 9 will be graded before the deadline of the submission of grades. No guarantees kapag ka lumampas ng June 9 yung submission nyo. So chances are you might get an incomplete kapag ka meron pa kayong pinasa after June 9. Okay, but I'll try to be as lenient as possible. Okay? So I think that's all that I want to say for today. So see you. Let's just meet each other again on Tuesday. And until then, guys, keep safe. Stay dry. Pero wag pa lang stay dry. Baka gusto yung maligo sa ulan or something. But just enjoy the weekend, all right? And let's see each other again on Tuesday. Bye, everyone.